Have a look at this beam. So we have a simply supported beam. There is a uniformly distributed load over the half the span, you can say. Then there is a point load of q newtons. What we wish to work out is the deflection at this very point. Let's say that this point is your point C, and we wish to find its vertical displacement or deflection, whatever you may call it. This YC is something that we wish to calculate. Now, how can you do this without making the math messier, without making fancy equations as you did in Macaulay? So the easiest way is to use the formula sheet, to be honest. However, you don't have a formula sheet for a simply supported beam having some UDL, having a point load, and let's say I make another loading over here and I ask you what is the deflection at point C. Would you be able to do that? Well, I'm afraid not. The easiest method is the method of superposition, and let me just demonstrate this to you in the next 30 seconds. And here we go. So we are going to say that we are going to think or perceive this beam being divided into two parts or two different loading conditions. Number one is where the beam is simply subjected to the uniformly distributed load, and we have the formulas through which we can calculate the deflection at C. Okay, for case number one, you can say. In the second case, we are going to forget the UDL and we are going to simply observe the deflection due to this point load. Have a look. This is what we'll try to do, and we'll find the corresponding deflection for this arrangement too. Now, when you have these two values, what you simply need to do is you'll need to write YC is equal to YC for case 1 plus YC for case 2. This, my friends, is your method of superposition. Okay, and in order to discuss this, I have got 3 beautiful examples lined up. Let's check them out one by one. So this is your example number 1, where there is a simply supported beam with some UDL for 4 meter length, and then there is a point load. In the second problem, we'll see a cantilever beam. The UDL is for a length of 6 feet, and you need to find again the slope and deflection. Very important problem. This is an foot-pound-second system, so you'll have to watch this. Okay, and the third problem is also quite simple, and this is where you are going to come across a triangularly varying load. Okay, all set. Here we go. Problem number 1. And by the way, throughout, if you have been watching my lectures on mechanics of solids, one thing that you must realize is that I have been using this book, that is Mechanics of Materials, written by Dr. R.C. Hibbler, to refer to it. As a mechanical engineer or as a civil engineer, you must own a copy of it. I have a physical copy of it. You should also have it. Okay, here we go. Let's start. So what is the objective? The objective is to determine the displacement at point C and the slope at the support A. Okay, the displacement at point C and the slope at the support. So the slope at point A has to be found and the deflection at C. So if I were to make the elastic curve, elastic curve is basically an assessment as to how the beam would bend after the loadings have been applied. Okay, it is an exaggerated form. The beam does not bend in that fashion, as you can see on screen. Okay, now students, I want you to notice this is the slope that I wish to work out, theta A, the angle that the tangent makes with the horizontal at this very point on the elastic curve. That's slope at A. Secondly, there is this deflection or downward displacement, you can say. Okay, that's YC. So these are the two quantities that we need to work out. How do we begin? We split up the beam into two parts or two different loading conditions. In loading condition number 1, you can see we just have this UDL and nothing else. Okay, and in loading number 2, you'll see that we just have the point load. Okay, by the way, you must see this. If I make the elastic curve, it would be something like this. It's a rough estimate. Okay, don't be serious about this, right? This is the angle that the tangent makes at this very point on the elastic curve with the horizontal. And secondly, this is the deflection at point C. because of this loading. Okay. Now, this is your case number one. In case number two, you have an arrangement where we are assuming that the beam is subjected to just a single point load of magnitude 8 kilonewton. Let's say that the elastic curve is of this sort. Again, these are the slopes and deflections. If you notice, I have used the subscript 1 both in slope and deflection over here. Okay, and subscript 2 both in case of slope and deflection over here. Okay, so take note of it. Now comes the time where you have to start learning how to use these formulas. Here we go. Let me just show this to you. I have a PDF, and by the way, if you own a copy of this book, you can see all of these formulas right at the back. This is appendix C, by the way. Okay, so if you recall, let me go back to this. And would it be possible to open the PDF here? I think we should be able to do this. Yeah. So what do we have? We simply have, let me squeeze this. Okay. You guys can zoom in by pinching your screen. There is just a uniformly distributed load for half the length of the beam. So do we have a formula of this kind? Yes, there is a formula. So in the formula, you can see the slope at this very point, at this very location. I think we'll have to zoom in. Okay, we want the slope at this very location. Let me zoom in. That is theta 1. Theta 1 is negative 3WL cube over 128 EI. That's the first formula that I'll use. Secondly, I want a deflection at this very point. That means at a distance of L over 2. So this essentially can be calculated by this expression. Okay, this V written is nothing but the vertical displacement. So this is the formula that I'll use. Minus 5WL raised to 4 over 768 EI. The negative sign simply indicates that the displacement is downwards, and this negative sign simply indicates that the angle measured over here is clockwise with respect to this horizontal line. Okay, so with that being said, I think we can begin. Here we go. Let me write down the formulas. Happy? Okay, done. Now what to do? What you now need to do is you need to plug in the value of W. That's 2 kilonewton per meter. Okay, here it is. And the value of this L, if you notice, 4 plus 4 will give you the value as 8. Done. When you plug in all the values, you get an expression in terms of EI. Here it is. Okay. Now what? Now what shall we do? Have a look. We have also seen the formula for displacement for this very case. Case number 1. So let me write it down. It was something 5WL raised to 4 over 768 EI. Okay. Now you need to plug in the value of W as this and L as 4 and just try doing it. This is what you get. Easy. Okay. Now you need to solve this. You're going to get a simplified version. This is that simplified version. Okay. So case number 1, the calculations have been made. We were supposed to calculate theta A for case 1. When the beam is subjected to just the UDL, this is the value which we got. Secondly, we were also supposed to calculate a vertical displacement when the beam is just subjected to the UDL for a 4 meter span. This is the value that we got. So far, so good. Okay. Case number 2. Now you need to focus here, students, on this very diagram. Okay. So how do we do this? This essentially is the case of a simply supported beam with a point load at the center. Okay. So I am going to use this formula sheet again, and I'm going to search for this case. Have a look. A simply supported beam with a point load at center. Here it is. Case number 1. Very basic. This is the value of slope and this is the maximum deflection. Obviously, the slope is here. That's the maximum slope that we are going to use, and the maximum deflection is going to be just below or just where the load is acting. Okay, minus PL cube upon 48 EI. So I'll be using these two formulas. Please note that. Here we go. Case number 2. Okay, what is P? So P here is 8. So you have to plug in 8. What is L? L is 4 plus 4, that is 8. So 8 times of 8 square. Let me write down and let us simplify this. This is what you get. That's the slope on a simply supported beam with just a point load acting centrally, okay, on one end. Next, we are going to calculate this deflection. Here we go. That's the formula if you recall. Now you need to plug in the value. P is 8, okay. L is 8 again, 4 plus 4. So when you plug in all of these values, what you get is an expression like this. Okay, now coming back to the point. What did we want? We want the total deflection, we want the total slope. Now, the idea of method of superposition is very simple. Okay, you have these two cases, you superimpose these two cases, okay, over each other, so that you have an arrangement like this. When you do that, you are essentially adding these two slopes, you are adding these two deflections. Since both of the slopes are sort of in the clockwise nature, have been measured clockwise, this is also measured clockwise, so the overall effect will be positive. And this is also downward, this is also downward, so the overall effect will be, I mean, you can assume that the downward direction is negative. It's your choice. Okay, so if both of them are in the same direction, they would add up, right? Let's do it. Let me make some space. Let's do it. So this is how you need to achieve the final values. So that's the slope, and this over here represents the deflection. This is just problem number 1, right? Do try this on your own. Okay. All right. Now, second problem is very interesting because you'll also get to understand how the tables can be used. Tables for different I sections can be used. Have a look. So this is based on a cantilever beam, and give me a moment. That's based on a cantilever beam, and have a look. Let me zoom into this. So you have a W10 by 15. This is, I mean, this designation is for a wide flange. I'll come to that. It is made up of A36 steel. So do you know the mechanical properties? So far you don't. Okay. But I'll show you how those properties can be figured out, right? Using a table, of course. Is subjected to the loading as shown. So there is this cantilever beam. All the units, please note, are in foot, pound, and seconds. FPS systems, basically. So this is kilo pound force, if you don't recall. So students in India, I mean, they work in SI units, and I mean, globally SI units is followed. But yes, in the US, still people follow the FPS systems, even in UK as well. Okay, so both these systems are being followed simultaneously. Anyway, so this also is an example to make you aware or get you familiar with this kind of system. Okay, all right. So that's a cantilever beam. It is subjected to the loading as shown. Okay, so there is just this uniformly distributed load. We need to determine the slope and displacement at its end B. It is at this very point we need to figure out the slope and displacement. How do you do this? So let me make the elastic curve. Have a look. What are your comments on this elastic curve? Have a look. Let me zoom in. If you notice the elastic curve that I have made, it looks like a curve genuinely between these 2 points, isn't it? And once you go beyond this point, that means beyond the UDL, there is no loading. Therefore, this remains absolutely straight, right? So that's the core idea, how you can solve this very case. Okay, so it's very simple. You need to search a formula for a cantilever beam carrying a UDL for half its span, okay, from the fixed end. That's what you need to do. Okay, so I think I should help you with this. Let me have my formula sheet. Here it is, and let me zoom out. That's a cantilever beam. Notice. Here we go. This is what we are searching for. Let me zoom out slightly. Have a look. Oh. This is a uniformly distributed load. That's a cantilever beam. The slope, this over here represents the maximum slope. So one of the formulas is minus WL cube over 40 ATI. Secondly, the maximum deflection is minus 7 WL raised to 4 upon 384 EI. Okay, and to be honest, the slope at this very point is equal to the slope at this very point because it's a straight line. Okay, all right, so we have the maximum deflection as well. I think I'll write down both of these. Let me open my PowerPoint, and yeah, basically this is what needs to be calculated. That is slope at B and the deflection at B. If you notice, the deflection at B is this much. That's the deflection at B. How do you calculate this deflection? You can think of this displacement to be divided into two parts. First is this part, the second is this part. This part over here can be thought of as a displacement at C, that is YC. Okay, this is the deflection I'm talking about. You can think of this as YC, right? Anyway, I have the entire solution. Have a look. This is interesting. Here we go. So I've written down the formula. Theta B is equal to WL cube over 48 EI. Okay. Let me show it to you again. WL cube over 48 EI. Negative sign simply indicates that it has been measured clockwise. Okay. What's next? So plug in the value. This is 3 kip per foot. Plug it in over here. And by the way, the length of the beam is 6 plus 6, that is 12. For sure. You simplify this. Okay. Please notice this is kip, kilopound force, dot feet square. I'll explain you why all of a sudden it should have been feet cube. How has this been converted into feet square? There is a proper rationale behind it. Okay. I'll come to that part. So far, so good. That's the value which we've got. Secondly, we also have the formula for deflection. But before getting into the part of deflection, let me simply calculate from tables. How did I get this value? Because I have been we've been instructed that we are having a cantilever beam that is W10 by 15 and it is made up of A36 steel. So its mechanical property and its geometrical property can be worked out. Both of them. How? Have a look. This is 10 cross 15, W10 cross 15. So let me open the geometrical property. W10 cross 15. So this starts from W24 cross 104. This is for an I beam. Okay. W10 cross 15, 10 cross 15. Okay. Got it. Here it is. This is W10 cross 15. Okay. So this over here, 68.9 is the value of second moment of area, moment of inertia, to be honest. Okay. Here it is. This is what we needed, the value of I. However, it has been given in the FPS system, that is inch raised to the fourth power. Okay. Secondly, you also need the mechanical property. If you notice, we have been instructed that the material of the beam is A36. So again, all of these can be found out in the tables which have been provided as appendices at the end of the book. Go ahead. Okay. So it is, if you notice, A36. Where is A36? Here it is, A36. What do we want? You want the value of E, Young's moduli. The value of Young's moduli is 200 gigapascals. Okay, so we have both the values. Now all you need to do is to plug in these two values. Okay, that is 68.9 inch raised to the fourth power and 200 GPa. By the way, since everything is in foot pound and second, so you make the necessary conversion from 200 GPa. This will be 29,000 KSI. When I say KSI is kilo pound force per square inch. Okay, that's the conversion. Now you need to plug in these two values over here and you need to get the exact value or numerical value of the slope. 0.00778 radians. Okay, so that's just the first part of the solution. In the second part, we're going to find the displacement over here. How do you find the displacement? What is the formula that you're going to use? Okay, 7WL raised to 4 over 384 EI. You can clearly see this is we searched for the formula based on the question that we are solving, and you simply now need to plug in the values. Let me show it to you again. That's the formula sheet. Okay, this is the case and here it is. 7WL raised to 4 over 384 EI. Negative sign simply indicates that the deflection is downwards. Okay, here we go. So plug in the values. Okay, so 384E, that is 29,000. I is 68.9. Everything is in feet, pound, and inches. Right. Yeah, as far as WL raised to 4 is concerned, you can keep the value W as 3 kip per feet and L as 6 plus 6, that is 12. So plug in the values. Okay, I've simplified this part and it worked out as this much. Now, what are the units of numerator and denominator? Can you work it out? This is something that I want you to pause the video and think about it. Do give it a thought. Okay, let me show this to you. Focus on the denominator. The denominator has essentially these two quantities, that is E and I. Okay, now what can you do with this? E and I. Here we go. KSI, E is in KSI, you can see this, and I is in inch raised to the 4th power. Okay, so the unit for denominator is pretty simple. You can write it over here. Secondly, as far as the numerator is concerned, we have got WL raised to the 4th power. So W is in kilo pound force per feet, and L raised to 4, that is feet raised to 4. This is L, by the way, it is written in feet. So this is feet raised to the 4th power. You need to do a conversion over here, right? You need to convert this feet to inches. And by the way, if you simplify this, this is going to be, this will cancel each other out, fit, and this will be the 3rd power. So you have an expression of that sort. Okay, let me write it over here. Isn't it easy? So this essentially is kip. The numerator I'm talking about, kip dot feet cube. 1 feet is 12 inches, and that's why you see that there is a cube over here. If I can zoom into this, that is what I'm seeing. Got it? Great. Great. Wonderful. Now, all you need to do is you need to solve this, and you are going to get the corresponding value in inches. The deflection in inches. And it's fairly simple. Here it is. That's the value. So problem number 2 is done. Okay. Problem number 3. It may come across as intimidating because of a triangularly varying load, but it isn't. Okay. Since we are using just the formula sheet, and this is the method of superposition, everything becomes easy when you split it up and solve. Okay. Divide and conquer. Anyway. Okay. These were the data taken. Right. So you've got a triangularly varying load. Have a look. Very interesting case. Determine the displacement at the end C of the cantilever beam shown in the figure. EI is constant. We need to find the displacement at C. Okay. If you have a look over here, we really don't have any formula, do we? It's a cantilever beam, you can see. Okay. The problem that we've been given is a cantilever beam, and the uniformly varying load is not through the entire span. However, it is for a particular section of the span, just for 6 meters, or you can say 75% of the span. How do you figure out the slope and deflection over here? It's quite challenging. Okay. Or how do you figure out the deflection at C? Quite challenging. Okay. So you've got to use a bit of trigonometry here. You've got to use a bit of a relationship that is between the arc length, radius, and the angles, right? I'll demonstrate everything to you. You stay with me right till the end. This is going to be very, very interesting. Here we go. So how do you think the elastic curve would look like? This is how it would look. Let me show this to you again. It's a curve. It's a curve, looks like a curve from here to here, and then it becomes absolutely straight. Okay, fair enough. Now, this is what you need to work out. Okay. How do you do that? For this, what we'll do is we are going to find the deflection at B. Just listen to this. The deflection at B. And then we are going to add PQ to it. Once you add PQ to this deflection of B, you are going to get the deflection at C. Let me write it down mathematically. Okay. But again, the question is, how can you calculate the deflection at B? Isn't this challenging? Do we have a formula for it? Yes, we do. Have a look at this formula sheet for a cantilever beam and try to identify Try to identify. Isn't this a case of a uniformly varying load? Give me a moment. This is a case of uniformly varying load, isn't it? Let me zoom in further. So what do we want? We are going to calculate two quantities here. We are going to figure out the slope and we are going to figure out the deflection as well. Okay. So as far as the slope is concerned, this slope is equal to WL cube over 24 EI. Okay. And as far as the deflection is concerned, it is WL raised to 4 over 38 EI. Again, the negative sign indicated, you know the meaning, right? Okay. Let me go back to the slide. Here we go. How do we proceed? So this is what I have just written. What I can do further is this. Have a look. By the way, the beam should never deflect in this fashion. Okay. If it does, then your job may be in danger. So let's say this and this. It is part of a circle, let's say, and the angle subtended is theta. This is r and this is the arc length. So you know a relationship that says that theta is equal to arc length over radius, or arc length is equal to theta times of radius. So following this philosophy, you can figure out theta b. If you notice, theta b can be written as theta b is equal to arc length, that is pq, times of radius. Okay, the radius can be taken as 2 meters. This is one way of perceiving it. Since you can only do this if the angle subtended, this angle is, we are assuming that these two lengths are very, very close to each other. Then you can apply this logic. Okay, makes sense. Secondly, you can apply a bit of trigonometry. Have a look. So you've got a right angle triangle. Let me zoom in. So if this is angle theta, that's the opposite, that's adjacent, that's the hypotenuse. In order to find tan theta is simple. Tan theta is basically opposite over adjacent, perpendicular over base. Right? So if this angle theta is very, very small, okay, the beam deflection, these angles are very, very small, to be honest, right? So it is very safe to assume theta as tan theta, right? So theta can also be written as O over A, opposite over adjacent. So, if you use this philosophy or this philosophy, you are going to get the same value of PQ. What do we want? We want PQ. That means, PQ, let me write it down. PQ based on this philosophy is equal to theta times of A. Okay, adjacent. This is that adjacent, if you notice. That is 2. So theta times of 2. Okay, and where are we essentially calculating theta? Theta is calculated at B. So that is theta B times of 2. Right? And I'll write it over here. Okay, length BC, which apparently is 2. So far, so good. Now, what's next? Okay. I think you've seen those formulas. I'll write down the formulas for YB. Okay. And by the way, okay, I've written it for slope first of all. So this is WL cube over 24 EI. Now, if you notice, there must be some confusion inside your head that this is the L. That means L essentially is the length of the uniformly varying load. The length of the uniformly varying load. Okay, where it starts and where it ends. The distance between the two. That's L for you. So if you notice, as far as our problem is concerned, this is where it starts and this is where it ends. And the distance between them is 6 meters, which is why WL cube over 24 EI. Okay, 6 cube. That's the region. That's the first thing. Secondly, this theta, that's the value. Okay, so we are going to figure out the answer in terms of EI, you can say. Now, what is the next step? In the next step, we'll try to figure out this part, PQ. We are going to multiply LBC with theta B. Okay, there we go. YB. Okay, do figure out this YB as well. Again, let me go back to the formula. This is WL raised to 4 over 30 EI. Let me show this to you. Let me make a confirmation. WL raised to 4 over 30 EI. Right? So let me plug in the values. This is what you get. So essentially you have YB, that's YB, which you are going to plug in over here. You have theta B, this is theta B, which you are going to plug in over here. You also have LBC, that is 2 meters, which you are going to plug in over here. Once you do all of this, this is what you get. It's fairly simple. I don't have to do the math for you. It's very easy, and you can see that's your final answer. Okay, obviously the deflection is going to be downwards because the loading is downwards, right? So this is how you have to fine tune your brain whenever you're using the method of superposition. Again, the prerequisite is you need to understand how to use the formula table, how to use the geometrical properties, how to use the mechanical properties. This is the geometrical property, this is the mechanical property, and this is the formula table, which I'm sure will be given or will be allowed in the examination hall. Okay, should you be writing or taking a test on method of superposition. So guys, that was all from my side for today. And should you have any doubts, do write them down in the comment section below. I will be very happy to answer them. Okay, so this is Manas Patnaik signing off. Take care. Have a nice day. Thank you very much.